Hi, this is Brian Long. I'm a freelance consultant developer trainer. I work with Delphi and various other development tools, and in this session we're going to be using Delphi and looking at how we can access various iOS APIs. When building Delphi mobile applications, the FM application framework provides you with the basic structures required to build a nice, attractive looking user interface and provide data access and so forth, but sometimes it's useful to be able to reach out to the operating system and access more of what's available that isn't currently wrapped up in your development tool. So, we're going to have a look at the mechanism that's used to interface between Delphi and the ObjectiveC APIs in iOS, and that mechanism is called the ObjectiveC Bridge. We'll have a little look at the differences between Delphi and ObjectiveC. We'll have a browse through the implementation of the ObjectiveC Bridge, see which classes and interfaces are important, which ones come into play, how we use them, have a look at a couple of helpers offered in the runtime library, and then look at some examples of doing some iOS things by the use of the APIs. Both Objective-C and Delphi are compiled languages. They both compile down to the native machine instructions on the device they're running on, so that'll be ARM instructions in the case of iPhones, iPod Touches and iPads, and also Intel instructions in the case of the iOS simulator. They have many things in common. They're both modern compiled languages. The primary differences come from the fact that Delphi is Pascal-based and Objective-C is C-based, so consequently operations like string concatenation and so on are a bit of a doddle in Delphi, but there's still a bit of a bind in Objective-C. The distinctions between the languages are, other than that, fairly nominal. However, it is worth noting that both of these languages do support automatic reference counting. So Objective-C has automatic reference counting as covered here in the iOS reference site, and also Delphi supports automatic reference counting in the mobile compilers. So they both deal with automatically managing their own objects. So Delphi will automatically dispense and tidy away any Delphi objects when they go out of scope or when the reference count goes down to 0. Similarly for Objective-C, Objective-C will make sure that Objective-C objects get automatically reference counted and get tidied away when their reference count gets down to 0. However, it is quite important to note that when interacting between Delphi and Objective-C, Delphi's internal references to Objective-C objects are managed via pointers, and as a consequence, whilst both systems do have automatic reference counting, Delphi will only automatically reference count its own objects. If you cause an Objective-C object to come into existence, then it's down to you to manage the reference counts manually, because the Objective-C reference counting won't be operational. And similarly, the Delphi automatic reference counting won't operate against the Objective-C object at the other end of the pointer. So there's some key issues there that we'll see come into play. Let's take a look at how Delphi does interact with Objective-C. Let's take a look at the Objective-C Bridge. In the Delphi installation directory, there is a source subdirectory. In the source subdirectory, there is a runtime library subdirectory, and in the runtime library subdirectory, we have a variety of additional subdirectories for the various platforms. Now, the iOS and the OS X subdirectories both offer some Objective-C support, and in fact the Objective-C Bridge is shared between the iOS platforms and the OS X platform. So you'll find the Objective-C Bridge implementation inside of the OS X subdirectory. In fact, we'll find it here, macapi.objective-c. So let's load this file into Delphi and take a little browse through it. In this unit, let's just get the structure window up so we can get an overview of things. In this unit we have a number of interfaces, a number of classes, and lots of unimportant implementation details with regards to the Objective-C Bridge. Let's just run over the interfaces and classes just to give you a flavour. It's not that important to be fully on top of all the details, but it just gives you a flavour. It paints a picture of how the Objective-C Bridge operates. Whenever we import a class using the Objective-C Bridge, we split the class functions from the instance functions, as we'll see. And when we look at the interfaces available, there is an iObjective-C instance interface and an iObjective-C class interface, both of which inherits from the common iObjective-C base interface. So these two interfaces, iObjective-C class, iObjective-C instance, separate or are used to separate the definitions of the instance functions from the class functions. The class that makes use of these two interfaces is a class, let's see if we can find it, TOC generic import. So T ObjectiveC generic import, and you can see it is a generic class, and it takes as its generic types an example of an iObjectiveC class interface and an iObjectiveC instance interface. So it takes the two interfaces which define all of the class functions and all of the instance functions, and it merges them together into one Delphi accessible bridge class. Now, this bridge class happens to implement another interface as well, an interface called iLocalObject. Now, iLocalObject crops up here and there. The purpose of iLocalObject always being implemented by any class from the bridge which represents an Objective-C object is that it provides a member function called getObjectID. This member gives back a reference to the actual Objective-C object as an opaque pointer. So anytime that you actually need to reference the real Objective-C object as opposed to the Delphi wrapper of the Objective-C object, you can use getObjectID and it will return you back the opaque pointer to the Objective-C object. So iLocalObject is implemented by that bridge class, TOC generic import. It's also implemented by another class called TOC local. If you ever wish to implement, say, an Objective-C interface, then you would inherit from TOC local, such that the system, the bridge system, understands that this class represents an interface that really lives over on the Objective-C side of the fence. iLocalObject is implemented here such that we do have a way of getting access to the Objective-C object via the opaque pointer, and we'll see this class and we'll see TOC generic import in use as we go through. So probably, rather than get bogged down in the details, it would be an idea to look at an example of a bridge class and just map it back to what we've just seen with regards to the interfaces and the bridge class. When we do, we'll see some of these members come into play. So for example, there's a member alloc, which will actually allocate the Objective-C object on the Objective-C side. There is a class function called create, which is like a combination of calling alloc, which allocates the memory, and then calls the most simple parameterless constructor. Typically, you'll want to call various customized parameterized constructors, which will be implemented as class methods called init something something something. When you do wish to access a class member, you will make use of the OC class property. That gives you access to, well, as you can see here, it's of type C, where C was the parameterized Objective-C class interface. So it gives you access to the interface, and then from there you can call any of the class functions available in the Objective-C object. And finally, the other member that we'll bump into is wrap. If you get handed an opaque pointer to an Objective-C object, which will be typed as a pointer, you can pass it into wrap and it will produce you a bridge class wrapping up that Objective-C object. Okay, let's look at an example. iOS is subdivided into a variety of what Apple calls frameworks. If you look up the iOS developer library on Apple's website, you can have a little browse down and you can see the frameworks, and you can see that we've got lots of frameworks including UIKit, which covers all the basic UI stuff, MapKit for the mapping stuff, we've got Core Location for the GPS and location aware stuff, and so on and so on. There are lots and lots of different frameworks, and some of them have been partly imported into Delphi, primarily based upon the requirements of the FM application platform. UIKit, there is quite a good amount of stuff imported, so we'll pick upon a class which resides in the UIKit framework. Specifically, we'll pick upon the UIScreen class. Now, the UIScreen class is a class that has an import available in Delphi, and we can see here in the documentation for it, the Apple documentation, that UIScreen inherits from NSObject. And NSObject is the basic object in the Objective-C runtime system. So it's the equivalent of Delphi's T-object, where everything inherits from that. So it inherits from NSObject, and it offers up some properties and some class methods and some instance methods. The properties it offers, for example, brightness, the screen brightness, the bounds of the screen, what the current screen scaling is. We can also, using this class method here, get access to an instance of UIScreen representing the main screen, bearing in mind that you can have secondary screens. So the main screen class method will return us a UIScreen instance, so it saves us the trouble of allocating an object. It allocates it for us and returns it to us, and there are also one or two instance methods. The usefulness of which may vary. Let's have a look at how this is represented in Delphi. So we'll switch back over to Delphi. Actually, I'll switch over to Windows Explorer, and in Windows Explorer I'm looking here at the runtime library source directory, specifically the iOS subdirectory. And in here we can see there are a number of import units which correspond to a variety of the frameworks, so core location, core graphics, core audio, core video. What else have we got here? We've got UIKit. Right, so UIKit is where we're going to find UI screen. So we'll drag that into the editor, and UI screen is imported via two interfaces and a bridge class. So the two interfaces, as discussed before, we have one of them being the interface that defines the class functions. They are just members of this interface, but this interface represents class functions. So we have main screen and we have screens corresponding to main screen and screens. And then in the other interface, which represents all the instance methods, we have the standard instance methods and also the property readers and property writers. So bounds was a property. This is where we can read. It must be a read-only property because there's a bounds but not a set bounds. On the other hand, brightness, there's a reader, and set brightness, there's a writer. So we can see all of these imports listed out here, and then these two interfaces are merged together. UI screen class and UI screen are merged together by passing them into an inheritance of TOC generic import, giving us the TUI screen wrapper class or bridge class. Now, the interfaces, UI screen is inherited from NSObject. NSObject is another interface inside of Delphi which defines the instance methods for the basic ObjectiveC NSObject class. And in the case of the class member interface, UI screen class, that inherits from NSObject class, the corresponding interface that defines the class methods of NSObject. Okay, a couple of other things to mention. Perhaps these interfaces have interface identifiers, IIDs. Each one is unique. It's not a specific number. It's just a random unique number just to identify it for interface querying purposes. Also, generally, the parameters that get passed into these calls, or that we pass into calls, often where these parameters represent ObjectiveC objects, we will find they are of the appropriate type. So, for example, here, search bar is of type UI search bar, and let's see if we can find another one. View controller of type UI view controller. So, parameters do get wrapped into these ObjectiveC Bridge interfaces quite neatly. However, going back to wherever UI screen was, here, you might notice that the main screen function return value, even though the main screen function is designed to return a UI screen, what we find in the import class is that main screen is returning a pointer. Function returns don't get wrapped up in these nice interface wrappers. We just get a pointer to the raw ObjectiveC object, and it's down to us to take that pointer and to pass it into the wrap method of the appropriate bridge class, TUI screen, and that will then give us a UI screen interface reference. Okay, let's see this in action. I'm going to pull up a project which I've got for this session. Okay, so here we have a little form with a couple of items available in a list. A couple of items, too many by the looks of it. Okay, so the first couple involve UI screen, so let's take a little look at those. The event handlers for those two list box items clicks are sat here. They're both pretty much the same. There are just a couple of minor differences I thought would be worth highlighting. In the case of the first one, what we're doing is we're using that bridge class, which we just saw, and we're referring to the OC class property, which will then give us access to all of the class member functions. So that gives us access to main screen, but you'll recall that returns a pointer. So yep, as mentioned, we have to pass that into wrap, which is a method of our bridge class, and that then returns us an instance of the interface, the wrapper interface UI screen, which we can then store in a local variable. After that, we can then start talking to its properties, so we can read the bounds property, store that in a variable of the appropriate type, NSRect. This is one of many standard data types, NSRect. If we go and look at the definition for it, we can see that it's just a record defined in the foundation framework import unit. It's made of two other records, NSPoint and NSSize. So if we look at NSPoint, it's defined there, and if we look at NSSize, well, that's also just defined there. Okay, so having got the information, we can then pull out the X and the Y and the width and the height and display how big the screen is. Now, the reason there's two versions is because, well, the first one manually gets the main screen from the class member function of TUI screen and wraps it up and returns it as an interface. The second one takes advantage of a helper function that is provided inside of fmxhelpers.ios. So let's have a quick look inside of there. In fmxhelpers.ios we have a bunch of standard little wrappers which just make slightly more convenient certain operations which may or may not occur fairly often during iOS development when trying to reach out to the iOS API. So we do have main screen, which unsurprisingly as its implementation does, well, exactly what we just did really. There's also a similar method for getting access to the shared application. Every iOS application has a UI application object in it, and shared application is a helper which extracts that for us. Also, if you want to subscribe to various notifications going around the system, there's the default notification center. We've also got some helpers which translate strings. So when you've got an Objective-C string whose type is NSString, and you want to turn that into a Delphi string, well, you're going to need to pass that into NSStr to str, and that will do whatever is necessary to turn the Objective-C object into a Delphi piece of text. Similarly, there's another translation which goes the other way. So string to an NS string. That's not actually in this unit, so let's go and find where that one resides. Aha. So in the foundation unit there is an NSStr function which does the opposite. Odd that they're not in the same place, but this one takes a string and returns an NSString version of it, which you can then pass into iOS APIs. That goes ahead and does a similar sort of thing to what we did with the screen. It talks to the TNSString Bridge class, accesses the OC class member to allow us access to the class functions, and then calls string with characters and passes whatever it needs to in there. Anyway, not important. What's more important is getting back and checking out that, other than that, there are no differences between these event handlers. So let's just test this out. I'm going to run it against the simulator so we can readily see it on this screencast. Let's give it a quick run. Okay, so on this particular iOS simulator, the screen says it is 320 by 480 with a top left of 00, and of course the second button does exactly the same. So, back to the code. The next button was apparently going to be looking at UI device class. Now, this UI device snippet looks very similar to the UI screen snippet because it's accessing the TUI device bridge class and then accessing a class member called current device, which is going to return a suitably initialized and constructed UI device instance, which we wrap into a bridge class and store the interface thereof. In this case we're getting the model out of it, but I guess the reason that I popped in a device example is that this one then goes on to do some logging. Instead of a message box, it uses the standard OS logging mechanism, which on iOS and on OS 10, I think, is done by a call to nslog. Now, nslog's job, according to the Apple documentation, is to take a string and send it off to the log. The log will differ in its location depending upon whether you're working with a device or with the simulator. In the case of the simulator, then the logs will go into the console application, console.app. And if you're running on the device, then the logs will go into the console section of the organizer window for your device within the Xcode application. So you can get access to the logs in both cases, but the log takes a string and it's not as simple as you might expect. Typically, with the interfaces that you work with, the interfaces that represent iOS objects, then if a string is expected, you pass in an NS string, end of story. In the case of nslog, it's a function, it's not an interface, so it doesn't benefit from all the nice Objective-C Bridge work. As a consequence, nslog actually takes just a pointer. It's the underlying Objective-C pointer, a pointer to the string object itself, outside of any NSString Delphi wrapper. So consequently, what I've got here is, well, device.model does return an NS string. So model NS is a variable which will contain an NS string, and then in order to satisfy the requirements of NS log, what I need to do is to extract the underlying Objective-C object ID out of the NS string. So to do that, we cast it to an iLocal object. You'll recall that all bridge-related classes implement iLocal object, and once we've done that, we can call getObjectID, which gives us back the Objective-C pointer. With that, we can then pass that along to NSLog. NSLog is happy, and if we want to do the same sort of thing of taking the NS string but passing it to showMessage, well, then we'll need to turn the NS string into a Delphi string using the previously seen NSStr to str function. Let's see if this does the trick. No need to relaunch the application, it's still running in the simulator, so I'll switch over, tap on the UI device button, and it says iPhone Simulator, which is the model of the device that's currently running. Also, if we have a look in the console application, we'll see that API Stuff, which is the name of this project, has emitted a log of iPhone Simulator. Next on the list, alert views. Alert views are what iOS uses to display dialogues, little message boxes. So we've got a couple of examples, in fact 3 examples here of using alert views. So let's just take the simple case. The simple case, so something equivalent to a show message. UIAlertView, if we went and have a look at the definition of it, it's defined inside of the UIKit import unit, and it's got a whole bunch of members to allow you to initialize it with various attributes, or initialize it bare and have a bunch of properties that you can, or functions and procedures that you can call to set up the various attributes. And ultimately, once you've set up the UIAlertView, you end up calling show. So back in our code, well, what we're doing is we're using the bridge class and calling the create class function. Remember, it's not a constructor, it's a class function that calls alloc to allocate the memory to instantiate the object, and then it calls init, the parameterless construction method, in order to bring us a default alert view object. So this is not using a parameterized constructor, and consequently we then have to go through setting all of the attributes that we want to set explicitly. So set the title, set the message, specify an appropriate button, and then launch it. And also, because I have caused the UIAlertView object to be allocated, the reference count will have been bumped up. So I need to counteract that at the end of my use of this object, so I call release to knock the reference count back down, and because that will then take it to 0, the object on the Objective-C side of things will get destroyed. So when you allocate an object, it essentially retains a reference, or increments the reference count to the object, and when you're finished with it, you have to call release to knock it down. Outside of that, if you wanted to make sure that an Objective-C object hangs around, you can explicitly call retain. And when you wish to undo the act of calling retain, you can call release. So retain and release increment and decrement the reference count. So this code is designed to try and be resource friendly and memory management secure, and so we should get a little message box with a title and a message and an OK button. So let's check how this operates. Back to the simulator, hit the UIAlertView button, and sure enough we get a message. So nothing too unusual there. We are making use of the bridge class, we're allocating and calling a parameterless constructor. We could do this a slightly different way, and in fact we will do it a slightly different way when we actually allocate it separately to initializing it in the next example. But it is worth noting again that to pass strings through to Objective-C, you do need to translate them to NS strings. Okay, the second example, not a million miles apart from the first example, but as I say, it does call alloc instead of create. So alloc will allocate the memory, but we have an unconstructed object. So what we then need to do is to take the object and call the object's init something something method, which will do the initialization of the object. In this case, I'm calling init with title because, well, init with title was pretty much the only init method we have. So init with title is a method that takes a variety of parameters to customize the initial state of the object. So in this case it takes a title, it also takes the message, it also takes a delegate, we'll come back to that, it also takes the cancel button and a starting point list of any other buttons that you want. We then again show it, and we make sure that once we're done with it, we release it. So if we switch back to the simulator and call UIAlertView2, we get exactly the same result. Good. So on to the final UIAlertView example. Now there's quite a bit more code here. In fact, what we have is a type being defined up here, and then a bunch of method implementations and so on and so on. Let's start down in the event handler. In the event handler, we start off with a UIAlertView reference as before, and then we construct an instance of an AlertViewDelegate. We'll come back to that. Then we allocate the alert view, and then we go through calling the alert view's construction method, passing in a bunch of text as before, but this time, where we previously passed in nil for a delegate, we are passing in the delegate object that we've constructed cast to a local object and then pulling out the object ID. So in other words, we're trying to get the reference to the ObjectiveC ID as represented by this delegate object, which we shall have a look at. After that, we're adding a few extra buttons and displaying it and tidying up as before. So the delegate is the key difference here. So let's go and have a look at this delegate class. So the class is defined to be something that inherits from TOC local. Now earlier on I mentioned that TOC local was a useful base class for any object that you wanted to implement an Objective-C interface in, and for Objective-C to then recognise this object as an implementation of that interface on its side of the fence. So in this case what we've got is an interface, or as Objective-C programmers would call it, a protocol. On Objective-C's side of the fence with a protocol, you don't actually have to implement all the methods, where of course in Delphi, given an interface, we do have to implement all the methods of that interface. But UIAlertViewDelegate is an example of a protocol or interface, and we're going to implement it over on this side, and we're going to implement these two methods here. Now, if we go and have a look at the definition of UIAlertViewDelegate, first of all, then we'll find that it's only really a partial implementation. There are a whole bundle of methods which they've skipped. Now, one of the reasons why they've skipped these additional methods is because maybe they just weren't important for the implementation of the FireMonkey message box routines. In addition, another slight complication that you get when trying to map Objective-C methods over to Delphi is the method naming scheme that Objective-C uses. With Objective-C, a method name isn't just the method name alone. The method name plus all of the names of its arguments are all conjoined with colons as separators to make one large, fully descriptive, unique name. As a consequence, the original base name of the method may well not be unique, and in fact in this case we can see that there are several methods that start with the name AlertView. They carry on and are distinguishable by their various argument names, but in Delphi's case that is not sufficient to uniquely identify various method overloads. Now, this is not an insurmountable problem in Delphi. In the Mac API Objective-C unit that we looked at the start of the session, there is a definition of a method name attribute, and you can apply the attribute to any given method when you're defining an interface or implementing that interface in a class. In the context of Objective-C interfaces, you can specify the actual Objective-C method name with all of its colons that your method represents. As a consequence, this issue with not being able to directly represent all Objective-C method names isn't that much of a problem. So the case in point here with this interface, I would imagine that really the methods have been left unimplemented for a combination of the two reasons. During the original development of the iOS support, perhaps the method name attribute did not exist, but also perhaps these additional methods weren't actually that important, so they didn't put much effort into finishing the job. Either way, we'll just work with the two methods which do exist, and we'll implement them, and indeed over in the source file we can see that that's exactly what I have done. I've implemented these two interface methods. I've declared a variable for the delegate to be referenced by. I have also implemented a little helper function which takes a Delphi string, turns it into an NS string, and then extracts the object ID of that NS string for the purposes of passing to NSLog. It's just a helper function to make NSLog calls easier. I could equally use log.d, but in this case NSLog was used. So, the purpose of the delegate is to respond to events, is to allow you to build in event handlers for the alert view. So, Objective-C uses delegates for its event handling mechanism. So, in this case, when the alert view is displayed and a button is clicked, the alert view clicked button at index method is triggered. So in this case, alert view clicked button at index is triggered, and we're able to say what is the index of the button, and depending upon whether it's 0, 1, 2 or 3, we know which button was pressed, so we can respond accordingly. And in this case I've used log.d calls as opposed to nslog calls. At the end of the method I've set the alert view's delegate to nil, and I've nilled my delegate object just to try and definitely be as careful as I can to be arc friendly on both sides of the fence. In the case that the alert view is actually cancelled in some means other than the cancel button, I've also handled that event and I've just logged the message alert view cancelled, and again tidied up responsibly. So this is an example of implementing a delegate protocol from Objective-C in a local object, passing a reference to that delegate implementation over to Objective-C, and let's find out whether it works. So, switching over to the simulator with the console sat next to it this time, we will press the button which invokes the alert view with a delegate hooked in, and we get a multi-choice question, yes, no, maybe, or cancel. If we press yes, the console says yes. If we press no, it says no. If we press maybe, it says maybe, and if we press cancel, it says cancel. So the delegate is operational. The implementation of the Objective-C interface has been done. Objective-C is seeing this in its implementation of Alert View, and we're getting the results we want. For every one of those buttons, we were also getting an additional message logged. We should be able to readily see where that comes from. Okay, that was an initial log at the beginning of the Alert View clicked button at index method. Okay, good. So the final functionality in this example is the network activity indicator. If you cause to occur some network traffic, such as loading a web page, calling a web service, you can, if you wish, indicate the fact to the user that network activity is ongoing by turning the network activity indicator on, and then when it's finished, turning the network activity indicator off again. The network activity indicator is the little spinning dial on the status bar, so let's see how this is implemented. This is simply a case of talking to the UI application object that every iOS application has, which is accessed via the shared application helper inside of fmx.helpers.ios, and then we can call a method, set network activity indicator visible, true or false. So let's just verify that works okay as well. So you'll notice nothing on the status bar spinning. Turn it on, that's network activity indicated. Turn it off again, it's off. Okay, so that example is now concluded. The next project we'll look at has a whole bunch of regular FireMonkey programming in it, but specifically it's got a couple of bits which should be interesting with regards to making use of the iOS API. The project itself has got a couple of pages in it. It's got a web browser page and it's got a GPS page. The web browser page just uses a regular web browser, nothing of interest in there. The GPS page does hook into the GPS sensor, or the location sensor. In addition, in order to display the location of the user, rather than use the web browser and look up an appropriate page on the web using a Google Maps API thing, it actually makes use of the iOS MapKit framework. So MapKit does offer on iOS an MK map view, which is a control specifically designed for displaying maps and putting annotations on said maps. So it seemed to make sense to want to make use of this map view. FireMonkey does not wrap up the map view, so I thought I'd test out the process of wrapping up a map view. So the project files again will be made available. I'll post them on my blog, but just briefly to go over it, the MapKit framework itself is not actually linked in by Delphi when doing a link process. So one of the first things we need to do if we want to talk to additional frameworks is to go into Tools Options and go to the SDK Manager, select your chosen SDK, 7 or 6.1, and scroll down to where all the frameworks are listed. You'll see there we have a list of frameworks including UIKit, Core Foundation, etc, 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 and by default there will not be MapKit listed. So in order to add in MapKit, we need to say, well, first of all, let's just look at an existing one. Copy the path, and then say we'll have a new one please, same path, and the framework name is MapKit. Now we need to do a refresh of the local cache in order to make sure that all the relevant files are now present. And now we're ready for using MapKit. Well, the MapKit framework local file is in the cache, but we do still need to tell the linker to link to it. In order to do that, we go into the project options and we go to the linker page, and probably in all configurations, just for the device, not the simulator, we need to pass in -framework as a flag and then pass in MapKit as a value. So the two units I've got here, fmx.mapview and fmx.mapview.ios, are designed based upon the file structure and class layout that I found in the sources for the web browser. The unit with the iOS suffix is the one that liaises with the iOS MapKit API, so perhaps we ought to have a little look in there. In here we have the guts of things, including the wrapper around the iOS classes. And of course the wrapper around the iOS classes has to talk to the representations of the iOS API. So for example, the delegate, which happens to implement MKMapViewDelegate, and the wrapper class, which references an MKMapView, MapKit interfaces themselves must be implemented somewhere. So let's go and have a look at where they are implemented. I've got a unit here called iOS API.MapKit. I have manually imported the MapKit API, or at least the portion of the MapKit API that I wanted to use for my example. I've got my class function interface and my instance function interface for the MapView class, and I've got a bridge class which binds the two together, and then I've defined my MapViewDelegate, which is an interface, and in order to specify that it's an interface that maps onto an ObjectiveC interface, I've inherited it from iObjectiveC. I've got all the relevant members in there. I've got only the members that I'm interested in inside of my MapView interface, so the ones relating to the annotation, the user location, center coordinates, possibly region, very little else other than setting the delegate. Over in my form unit, I have got a variable of type tMapView, and I've got a bunch of event handlers for the events that are surfaced from my delegate interface, and constructing the map view and setting up all the event handlers. Let's find out whether it works. Okay, when the application launches, we'll just check out the web browser, notice the network activity indication, nothing other of interest to say there. The GPS information page will pick up a location as specified in the simulator, which is Apple's HQ, and the MapKit will display the location and pop in an annotation with a little bit of caption that's custom specified in my code. So that seems to be fairly operative. The final project that we're going to look at is one I'm not going to look at in any detail at all. I'm really just going to show you it and then show you it running. It's an iOS project which involves no FireMonkey at all, so it's purely iOS APIs. Now, obviously, given Delphi's abilities and Delphi's features, building an application just in the iOS APIs isn't practical, and I'm not proposing that as a productive way forward at all. However, as a proof of concept and as a reference example, it's quite useful in as much as it shows quite a lot of techniques and shows how to do certain things in iOS. So we have in the project file, nothing much of interest, we have an application delegate, which all iOS applications require, and then we've got two view controllers. We have a master view controller, which inherits from UITableViewController and implements certain interfaces such as UITableViewDataSource. Here you'll notice the method name attribute. And we've also got a detail view controller. Again, the details I'm not going to run into. I'm just going to run it, and we'll just see it running and know that it works, and that will be that. The project files, again, will be distributed for the session. So we have a simple application which has a table view, has cells which we can select, and responds by bringing up a secondary screen. That is about it. Well, that's about all we've got time for in this session, so thanks very much for your attention. You've been watching Brian Long. If you need an extra pair of eyes or an extra pair of hands involved in your project, then please get in contact. But in the meantime, thanks very much. And if you've got any questions, I'll try and answer them now.
Yeah, there is no implicitly supported Bluetooth wrapper in the Delphi product because I guess the FM application framework doesn't require Bluetooth, so it wasn't a priority to get it imported. Whether or not it arrives in Delphi officially at some point in the future, who knows, but as of now, just like with any platform that Delphi supports, if you want to get access to the functionality, there's nothing stopping you tackling the problem yourself. And I think there was a link posted up. Michelle posted a link up for a work in progress or possibly a work in completion. I'm not quite exactly sure of the current status of support for Android Bluetooth imported. I haven't seen anything on iOS, but in essence, it's a project for the third-party world at this stage.
And where would they start looking at in the framework? You know?
Do you know, I don't even know where Bluetooth lives in the iOS framework list, but basically a bit of searching on your favorite search engine of choice to find out how you program Bluetooth on iOS. Go and look at the reference once you find out which framework that set of APIs lives in, and then it's a case of importing the APIs and then porting some code to use it, I guess. If you wanted to try and get Android and iOS support for a given piece of functionality which is available on both, then you would need to take some care to look at some of the examples already in the FMX source directories as to how you implement two things that are implemented differently on the two platforms but surface them via a common interface, such as done by the web browser and such as kind of done by that MapKit example, although that was clearly only done for iOS because MapKit only exists on iOS. But the surfacing of it via a control, which itself was platform agnostic, even though there was no Android implementation, serves as an example.
And I posted links to the Apple developer site Bluetooth for Core Bluetooth Framework, and also the developer Android connectivity Bluetooth starting point.
So this app would only work in iOS.
Yeah, that was the iOS API app. That is correct. It will only work in iOS as it stands because it is specifically talking to iOS APIs. It is perfectly feasible to split any API functionality into a unit of its own, surface that functionality via a class that implements an interface, and make use of that interface, which is implemented once for Android, once for iOS, in a platform-agnostic way. That's exactly how FireMonkey operates. But yeah, the example was specifically to show how you talk to a bunch of APIs specific to a platform for when that need arises. It's a separate problem to wrap it up in some sort of agnostic manner.
Am I able to add, for example, a UI scroll view into T-form and use aligning?
A UI scroll view is a CocoaTouch control. A Delphi form is a Delphi form, and aligning is a Delphi form property and code mechanism. So the scroll view is not going to be aware in the slightest of any of the attempts to align controls in FireMonkey. So the scroll view isn't going to follow suit. So no, not directly, not without stepping in and doing additional work.
So, and there was a question earlier. I don't see most of the questions here have already been answered, but there was a question about using a UI table view in a Delphi application.
I must have missed that question. UI table.
Sorry.
Sorry.
Yesterday, someone had asked about UI table view, and so.
Okay. The final app that I sort of cantered through within about 10 seconds did use a UI table view. So yeah, it's feasible to use it, but it's not supported in any wrapped up and productive manner as it currently stands in FireMonkey. So yes, it's possible, but how much effort you would like to go to facilitate that is debatable.
So you said in your next session you're doing a barcode scanner, which someone asked about in this session. There was an example also previously of a barcode scanner in XE4.
Yeah, there's a blog on Fernando Risotto's page. You can just search for barcode iOS Delphi XE4, and it used an iOS-specific library versus a cross-platform or multi-device library.
Sounds like if we combine that with your next session, then people can have barcode scanners on both platforms.
Yeah, that'll be an interesting project to try and unify the interface to both of those.
And you said all this code will be available on your website, which is blong.com, correct?
The website, the blog site is blog.blong.com, and I've just pressed the button to post the information up, so it should be there now.
I can use static lib from ObjectiveC in Delphi. Can I also use the XIB file, the zip file, and show it in Delphi?
Static libraries, let's have a little think about this. If memory serves correctly, Interbase is implemented via a static library, isn't it? Which therefore tells me that yes, you can do it, as long as you know the exports of the library to import, I guess. It has to be static because iOS doesn't allow dynamic libraries on a device. For zip files, or nib files actually I should call them, even though they've got an X at the front, I think they're still pronounced nib files. Nib files are the way iOS developers design their UIs in Interface Builder within Xcode. You can kind of use a nib file by passing it to the relevant API, which initiates a UI view with a nib file passed as a construction parameter or an input parameter. But again, that relies upon that whole windowing system revolving around a UI view. So I haven't found a convenient way of getting a nib file to work in conjunction with FireMonkey, but it is feasible. It's just not necessarily very maintainable. One of the things about Xcode is it allows a convenient syncing mechanism between the design and the source. You obviously won't have that syncing mechanism between Delphi and Interface Builder, and so there would be extra maintenance steps in addition. But yeah, the final project did, I'm pretty sure that final project uses a nib file. I'll have to double check. I do have one that does use a nib file, but I'm not sure if that final project was the one that did, thinking about it. But anyway, it is vaguely feasible one way or another.
Okay, so either that final project or something they can probably find on your blog in the future.
Ruslan was asking, is it possible to use third-party SDK like Facebook or other for iOS and Android and XE5? I mean, so many of those have REST interfaces that you can call when they're web services like Facebook or web technologies, and but there are developer, I'm not sure if the APIs, there was something that was presented yesterday at, I think it was Olaf, that showed the REST services library components connecting to Parse and Facebook,
right,
for doing things. So.
And then, Brian, that example you gave for importing MapKit could be used to import third-party framework as well?
I'm not, to be honest, I've not actually looked at how frameworks are stored on stored in terms of libraries and layout, but assuming that the third-party framework is implemented in the same sort of manner as one of the standard iOS frameworks, then as long as Delphi can see it in order to import the relevant, well, whatever it imports to link against, then I guess yes, but I don't actually know, not having followed the thread through particularly.